I was happy to come to this meeting and have something to say, but I thought, what could I add to the discussion? Because I don't work in an area that's directly founded by John von Neumann. So, you know, I'm sort of thinking, well, how am I going to make the connection, you know, to him? And I found out this morning that I'm one of those Americans who really didn't appreciate John von Neumann as the scientific genius that he was. And, you know, because I didn't hear about him much. I mean, I knew about the von Neumann architecture sort of as I was going through school, just more, but I didn't appreciate it well enough. And my story, though, is when I was studying for my PhD in math, I had to demonstrate that I could read mathematics in German. And so as part of the language requirements. And so I found a von Neumann book that had both a German and an English edition. And I used it to, you know, check my translations, you know, and see if I could translate properly. And, you know, and then another thing I learned this morning is that I was on one of those little tributaries that was far from the source. And so, you know, I probably should have paid more attention to the content of the book than just whether or not I could go back and forth. Anyway, so what am I going to do? I am the president of the IEEE Computational Intelligence Society, and but the buzzword today is AI. Right? Everybody's talking about AI. AI this, AI that. Is AI are we gonna have an AI Armageddon? You know, is there going to be Skynet all of a sudden, and you know, and humans are going to be destroyed? And there's an interesting, by the way, if you get IEEE Spectrum or you have access to IEEE Explorer, I don't know if it was just the most recent one. They had a nice 2-page article about many famous AI scientists today and where they sit on the AI Armageddon. You know, whether or not they think, first of all, AI is going to become a generally intelligent agent or not, and then whether it's going to cause destruction of the human race or not. You know, and it's interesting to see who fits where in there. You know, anyway, so that's in there. So my intention today is dissect is too big of a word. You know, I'm going to look at both artificial intelligence and what we say computational intelligence is, and hopefully look at some of the thoughts and accomplishments of Drs. von Neumann and Turing in this AI timeline, sort of how they interacted, what they, you know, from what I could gather, what their thought processes were, where they fit on the AI spectrum, and then of course, how do these large media models like ChatGPT or DALL-E, you know, or many others now that are out there. I mean, I found out now Photoshop has one. Word is going to have one soon. I mean, it already does projections of what you think you're going to type. Where do they fit into this picture? And in particular, I'm going to tell you what I believe would be the reaction of these two guys to ChatGPT, you know, in there. And it's just all pure speculation. So, you know, I mean, you can disagree completely, and that's okay with me. You know, just don't throw anything. And this is more, you know, I put this last bullet in there because it's really about me getting ready for this trip. You know, it's my meandering, you know, thought processes. And so I realized after I submitted the final version of this, I realized that I've repeated myself in here a few times because of different quotes I found in different places. And so just have to bear with me. So first thing I want to talk about is artificial versus computational intelligence. And so, you know, I mean, is it really a big deal? Because you've got AI, and then we of course, are the CI, you know. And so the guy in the back there points out that it depends on whom you ask this question to, whether there's a difference, and when you ask it. You know, so I wrote an editorial in our magazine about what's in a name, you know, whether AI and CI are really different. And so, of course, everybody's talking about AI now. You know, it's AI this and that. Everything we do now, if you can say, well, this is really AI, you know, you get, you know, it's good for funding. But of course, what is it? And so when I was a kid, academically speaking, you know, and I got into the electrical engineering department, and I was told, you need to teach a course on AI, you know, inside EE. And so I knew what it was at that time, and it was formal logic, basically. It was systems with propositions of discrete symbols manipulated through first-order predicate calculus, and maybe sometimes you had some probability, but it was always on the side. You know, you would do some probability calculations of the rules, and then you would report that separately. But the rules were all crisp. It was formal logic, and so that's what I taught, you know, till I found a book that also had the word AI, but it was really pattern recognition. And I thought, oh, I like that better. And there were languages that were built and machines that were built specifically to manipulate propositions of symbols. So you know, we had some symbolics machines, you know, very expensive for what they could do. I mean, but they ran Lisp in hardware, you know, and so it was that kind of environment that I thought, right? But when the IEEE, we started out as something called the Neural Nets Council in my gang, and then we became the Neural Nets Society, but they decided to change the name to the Computational Intelligence Society, and it made perfect sense to me that there was the difference between AI and CI, because CI, all of the underlying models for computational intelligence are based on numeric representation, non-symbolic representations, functional representation sometimes. So it was a nice crisp partition. Had AI over here, you had CI over here, and they won't meet, you know, in there, I thought. All right? And so the three pillars of our society as it's grown up are neural networks, fuzzy systems, and evolutionary computation, all of which are embedded with numeric representation. And we have a bunch of other related topics that come in here, including, for example, artificial life as part of, sort of spun off of evolutionary computation as a topic area within the IEEE. Right? That was supposed to be my symbol for that. I found those little digital bugs on the net. But was that ever the case, that they were really separate, that there was a dichotomy between these? And so then I thought, well, how far back should I go? So I went back to the place where AI got its name, right? And that was the 1955 proposal by John McCarthy and colleagues for the Dartmouth Conference, where they coined the term artificial intelligence as the science and engineering of making intelligent machines. Of course, none of that, I mean, it's a very circular kind of a definition. But in that proposal, the fledgling area of neuron networks were brought up. I mean, it wasn't the main result of the conference, as it turns out, because they focused mainly on symbolic logic, right? So that's one of the pillars of computational intelligence. So even back at McCarthy's time, the partition was never crisp, right? And in fact, it's not even a fuzzy partition. I'm you know, sort of my sub area within computational intelligence is fuzzy systems. It's not even fuzzy where you share belonging to either AI or CI, but they, you know, you can't, you still have a partition. You really have topics that have high typicality in both of them. For example, fuzzy systems, which came up in computational intelligence, really is one of the tools that people use in explainable AI now. I mean, you know, one of the big areas in AI is this idea of producing explanations, or being able to interpret what's going on, and fuzzy rules and fuzzy systems are one way to do that. So former president of CIS, Pablo Estevez, said, hey, let's go survey people and see what they think is the difference, because we couldn't get a good definition. We were trying to, back in his presidency, he was trying to write a statement, definition. This is what CI is, right? And this is what AI is, and they shall never meet. So he did, and what happened is you could imagine every possible configuration of a Venn diagram where you got one bubble is AI and one bubble is CI, and one's inside the other, one's, you know, they overlap. Some people said they don't overlap, you know. So it's every possible configuration. There was no consensus. So my position in that editorial was, don't worry about it. You know, who cares what you call it? You know, do good work, have fun, and if it helps to call something AI, you know, fuzzy systems AI or evolutionary computation AI, go ahead and do it. You know, I mean, we are the Computational Intelligence Society, but we are also the Society of AI. And I put these last three little bullets in there because even though David has absconded, since he was a past president of the Computer Society, is that there were 4 societies that got together to create the IEEE transactions on AI. You know, Computer Society, us, System Managed Cybernetics, the Signal Processing Society, and then the Robotics and Automation Society also kicked in. And we also, the first 4 of those also have created now the IEEE Conference on AI, just had the first version in this year, in 23, and the second one will be next time. This coming year. And so I felt pretty smug, as you can see in the picture, you know, that I kind of had this all figured out. By the way, that kind of shirt is what I'd rather be wearing right now, but I just somehow felt like I couldn't, but I guess I should have anyway. But wait a minute, you know, I'm being told, only back to 1956? What's the deal, you know, by these 2 guys. So, you know, I went back, I started doing a lot more reading. I've been reading and reading and reading and reading. And so, obviously, Alan Turing thought it would happen, right? That this would happen. And he, you know, had the design of the universal computing machine. David, I just put a word in for you, but I mentioned everybody that you had left. That could compute any computable sequence, right? The universal computer. And his basic principle, his basic thought on this was that it was only a matter of time and a matter of programming, right? That in fact he proposed constructing. He said, well, it's hard to imagine programming a human mind, you know, an adult human mind. So why not just construct a child's brain mind computer with lots of blank pages, and then come up with some learning methods. Right? And he said, of course, obviously, the reward-punishment scheme is the obvious way to, you know, that you might teach, but it's just too inefficient. So you needed some kind of intuition. You needed to have some learning methods that had intuition, which, of course, is nowadays, we're all talking about transfer learning, right? You learn a problem on a big data set, right, that's more or less similar to what you're doing, and then you transfer right into this. Now, I used to think that was all just baloney until I saw it works. You know, at least for deep nets, seems to work. But he never really worked that out. Right? I mean, these were more thought experiments at that time, you know, from what I've seen. So he came up then in that 1950s paper. He posed this question: can machines think? Right? And he said, well, both machine and think defy real definitions. So I need to find a surrogate problem to do this. And so he proposed the imitation game, right? That we've all heard of, even me, back, even though I didn't know sort of what it all entailed, but we've all heard of the Turing test, right? Where you ask whether or not a machine, well, first of all, it was whether a woman could imitate a man, was the original thing he proposed. And then he said, well, replace the woman by a machine, right in there. And well enough to fool an investigator, where the investigator would have at most a 70% chance of doing a proper ID in 5 minutes of conversation. okay? And his conjecture was that within 50 years, and with a storage capacity of 10 to the 9th, and that was, you know, the idea of storage capacity back then was a little different than we think about it now. I wasn't thinking of bytes necessarily, but units, right? Of 10 to the 9th, it was possible. This was his conjecture in that paper, right? But it was mostly a thought experiment at that time. All right, so this is the standard thing, you know, where you have the human and the machine and then the interrogator, right, being separated from them. But I like this version better, you know, where you're introducing your boyfriend to the parents, and they just want to know, going to ask a few questions to make sure you're a decent human being, you know. But how do you tell if the machine is really intelligent? You know, so so I started reading some bunch of other papers, right? And there's a lot of interesting work going on among the people who are thinking about AI, you know, as well as doing AI. I mean, as engineers, we like to do stuff. You know, we heard that early this afternoon, right? We're more vigorous than rigorous at times. And but the people who are thinking about it are struggling with ways to assess it. And I could not find, and maybe someone more knowledgeable than me knows this, but I don't think Dr. von Neumann had a recipe for detecting that. You know, I couldn't find anything about the imitation game in any of his writings, even though he and Turing worked together for a while at the IES, and he lobbied to get Turing a assistantship, I guess is what it was. You know, but he didn't address the imitation game. And so the current researchers are split. This is interesting reading, you know, that many on the pro side of these things being really intelligent, these new programs being really intelligent, say that these achievements give you at least a glimmer of reasoning, right? Because that's really what they were talking about. And on the con side, it's more, you know, it's more cautious to, you know, say that this is really intelligence that's going in there. You know, I put the references that I've been reading down at the bottom. And so there was apparently, I didn't even know this, but apparently there has been a prize every year offered for an annual Turing test, and for the source said for decades, until the guy who sponsored the prize died and the money ran out. So this was right about the time these large language models came into being. You know, the prize is done. Right? So there's no more doing that. And I guess the consensus is that the large language models like ChatGPT might win. I mean, because you don't have to fool every interrogator every time, right? You have to fool sort of the average interrogator with a probability of it, I guess, 30% of the time, right? So, and it's a short conversation. And so this group down here tested 1.5 million people. They played a version of the imitation game, but the large language models that they used, which I think was ChatGPT 4 in there, were sort of primed to act like a human. So they gave the ChatGPT a scenario. It says, your name is Mary, and you sometimes don't do calculations correctly, and you blah, 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 blah. And sometimes you're aggressive in your answers, and, you know, they would prime this thing to act more like a person, and the players identified the AI program 60% of the time. So only 60%, right? Only? I thought that was actually pretty good. But, you know, so they haven't quite done it, but you can increase the odds, you know, they were saying, if you know something about the large language models, how they're trained. So you try to put it into a situation that's similar but not exactly the same as what they're trained on, and they'll just spit out what they're trained on. You know, and so that's really how someone who's knowledgeable can game that system, right? but that's really, I mean, what we're asking these language models to do is to use deceit in their training. You know, and so is that really a goal for whether these are intelligent or not? It's kind of like a parlor trick. And so I thought I would ask ChatGPT what it thought, right? So, I mean, right, about its ability. So this was my question to ChatGPT. Could you pass Turing's imitation game? And so what it did is first it gave me a paragraph defining what the Turing test is, which of course is the first thing it spits out, you know, is you know, because it's just giving you words one after another based on probabilities. Then in the second one it says, whoa, this is a tough test, right? And even though I'm an advanced AI model, you know, it depends on lots of different things, right? It depends on the complexity of the conversation, who the judge is, blah, 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 right? And then it says also, I can't do this real time, even though, I mean, that's a hedge, right? The third paragraph's a hedge, right? Because it's saying, well, I can't do it real time, so I can't definitely claim I can do it. But look at the last sentence. But if you have any questions, hey, you know, I'm happy to carry on a conversation with you. You know, so, I mean, this is what ChatGPT told me. So I'm trying to figure out what does this artificially intelligent robot see when it looks in the mirror, right? And so what it's really seeing, these things are trained on who? On us, right? It's trained on everything that they can scrape off the web and everywhere else, and it's trained on. So they're just a reflection of what we've already said, right? And this is a pretty cool picture, I thought. You know, I created, but I got it out. I thought I could just go out to DALL-E and just give it a nice prompt. I wanted a DALL-E style painting, right? You know, I thought that was kind of cute, you know, to go out to DALL-E and do that, of an AI robot looking in a mirror, seeing a reflection of people, because that's the message I wanted to give. But I had to build this image out of several attempts at both people in a mirror, robots looking in a mirror, and then I had to use Photoshop and PowerPoint to actually get this to work. You know, so DALL-E would not have passed my visual Turing test in this particular case. Not that anybody else might either. Okay, and then I just as kind of wrap this part up is that these large language models, you know, have been shown to do really well on benchmark tests. I mean, they can take the LSAT, and you know, they can take the board exams for doctors, you know, things like that. And they can do really well on those things. And so now people are starting to look at these ways to try to measure a little bit more of reasoning, being able to get from one step to another. And this is a visual one where they show a bunch of demonstration pictures where they say, oh, take that first image, you get the second one. Then in the second column, same thing. And then show 3 more at the bottom and say, what would the output image be in each case? Most of us can figure it out pretty quickly. I don't want to put anybody on the spot, David, but anyway, it would be, you know, it's the kind of thing. This is and the tests that were run by this group, you know, of course, all these things are published on archive. You know, it's like, oh, put it on archive and then run on to the next topic. You know, so they're not none of these are refereed. But the large language models did poorly compared to the human subjects that they tested with this. So, how would Dr. von Neumann approach this topic, right? So I read carefully, you know, his book that was published posthumously, and a bunch of other articles about him. A lot of people have opined on this subject of his connection of, and we just heard it last talk, is, you know, the connection between the brain and the computer, right? And so, you know, a lot of this is going to be quotes that I lifted from the paper, that I sort of thought about this. He says he was looking for a way to understand the nervous system from the standpoint of a mathematician, and he admits that it's just systematic speculation, right? Just his thought process and going. We heard about his thought processes earlier. It was much more cautious than Turing. I mean, Turing was sort of out there saying, yeah, it's going to happen. It's just a matter of having enough people to program a big enough memory, right? And we'll get it all. And so, it was clear that he investigated these problems one by one, looking from the bottom up in there. And he said that the most immediate observation regarding the human nervous system, when he's talking about comparing the brain to a computer, is that its functioning is prima facie digital. So he says, oh yeah, the brain is a digital organ, but even though it's organized digitally, all of the complexities that we can handle as humans, you need at least there's an analog role or some kind of mixed role of analog and digital in this process, And so, he made a remark. He said, because look, the artificial automata need very high precision because of the air propagation, right? And, significant digits start getting lost if you don't have a big enough representation, whereas the nervous system has low precision, and yet we still do better at reasoning. It has much higher stability, the human nervous system. And so, he concludes that there's some radically different system of notation than the ones that we use in mathematics. And so he says you can't replicate human intelligence in a computer because evolution was needed to handle loads of uncertain and ambiguous information that we all deal with well. Oh, well, some of us better than others. And of course, McCulloch and Pitt's neurons had been defined and studied by the time he's writing this thing. So he understands some models, possible models, digital models for the neurons inside of a machine. So he could dig down deep into the components. Right? He was also worried about the fact that you might not be able to use formal logic in there because to represent human knowledge, because this would lead to the curse of infinite enumeration. And of course, as was pointed out earlier this morning, he was well aware of, and I realize now he proved the second theorem on the incompleteness theorem. And so, realizing this bothered him, saying, I think my impression is that he moved away from a purely logical approach to artificial intelligence in that case. And one of the examples he gave was an example on visual analogy. The fact, if you're trying to describe triangles, two rectilinear triangles, he said, man, there's just an infinite number of ways that you could vary them. They might not actually have all complete straight lines. They might, as you drew them, for example. But people would understand that they're triangles. The angles might not actually be, if you were drawing an isosceles triangle, for example, or a right triangle, the angles might not satisfy the right constraints perfectly, but people would get it. So if you were going to model all that, you need something more than just formal systems of rules, right? And so what I took from what he wrote is that he thought that you could use thermodynamics, the air probabilities and thermodynamics, to sort of model a lot of this uncertainty in there. I'm going to come back to that in a minute. Yeah, so he says the operation of logic have to be treated that allow things that have very low probability to still be true. And that was where he saw this inconsistency with formal logic systems, right, in there. And this author down here said, oh, well, I work in Bayesian networks, and so that's the answer. But I got a question mark there for myself. And of course, we've heard again, and I've read that you know, he has defined this artificial self-replicating automata with mutation in there. So he's built the mathematical foundations for artificial life, right, in this idea. And, you know, and he didn't get to the next step, which was to breed the automata which had more complexity than the one that it came from. He was able to do the mathematics to understand the sort of how the genome works, actually, right, the human genome, but not how you end up with more complexity than you started with. And so, blah, 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 blah. Yeah, this is one of those places where I just said the same thing over again. But this was 5 years before Watson and Crick that he did it. And matter of fact, one of those two guys, I want to say it's Watson, you know, said without John von Neumann, there would be no Watson and Crick. Because, you know, he built his automaton, the self-replicating automaton, had three parts. You have the functional part, the thing that actually does the work. You have a decoding section that takes a tape. This is kind of the reference to Turing thing. That takes a tape, reads the instructions, and builds the automaton. And then you have a device that takes the copy of the tape and inserts it somewhere else, right? And that's you know, essentially how the DNA works, right? So my take on this is that, you know, I was going to say the fathers of AI, but I read that you might call Turing the grandfather and von Neumann the father. I don't know, it just seems wrong. But somebody else thinks it's wrong too. Or else somebody else thinks it's right, and I'm in trouble. But I see this. I see these as kind of two different ways to attack the problem. You know, Turing was the optimist of symbolic logic, formal systems. You know, and he was using a top-down approach, where von Neumann was looking at the mechanisms, you know, the underlying mechanisms, and seeing if you could put it all together and get to that. Actually, I would rather say is that Professor von Neumann was the father of computational intelligence than artificial intelligence, and that way you don't have to argue about father and grandfather, you know, which one's which. Because he pioneered the analysis of biological and artificial neural networks, part of CIS. His work on cellular automata founded the area of artificial life, which is part of evolutionary computation in our definition. Again, you know, you can argue with me about that, but that's, you know, this idea of mutation, you know, in there. And he understood and proposed models for dealing with uncertainty in natural languages. Now, he was looking at using the probabilities in thermodynamic systems, but that was all before fuzzy sets became available. I'm going to believe, whether it's true or not, I'm going to believe that he would have thought kindly of fuzzy sets as looking at a different kind of uncertainty that's more related to the vagueness of natural language, as opposed to the probability that such and such was true. You know, and anyway, that's I'm going to say it. And he also, this idea that the nervous system has to have both digital and analog parts, it fits nicely with fuzzy systems because you have analog-like confidence values that you get from stimuli. You manipulate them via more or less analog operations, and then depending on the application, you harden it to a digital answer. Right? So what do I think these two guys would think of ChatGPT, you know, as an agent of artificial intelligence? Well, this is what I think. I mean, I think Dr. Turing would say, absolutely, it passed my test, right? Whereas I tried to make it not a complete thumbs down, you know, but my thought was always he's much more cautious about attributing these things to intelligence, and I think he would have seen it. And again, I'm projecting ChatGPT back into the early 1950s, right? And of course, what do you think? So finally, I'm done. I really want to thank Emory and everybody for inviting me and letting me ramble on for a while. And of course, this is as good as Google can help me say, and thank all of you for listening. And I was going to say, is there any questions or comments, but nobody's getting them. So that's good for me. All right. But this was created by Adobe's Firefly insert, which is also a large language media, a large media program that's inside Photoshop now. But it was the same prompt. There's no mirror, nothing. I just couldn't. I just could not get those programs to understand the idea of looking in a mirror, and seeing something other than themselves. I mean, if they did look in a mirror, it was a mirror like I had in that picture that I showed earlier. But anyway, I'm done. Thank you.